Dr. P here. In this video, I'm going to talk about how to deal with circular motion when you have forces that are at angles. The idea that you don't have just one complete force in the centripetal direction, but you have parts of forces in the centripetal direction. You see this problem most oftentimes when you have a car going around a track or a curve that is banked. And the other time you will see this is if you have something flying on the ceiling and it's traveling in a circle around. It's flying around in a circle hanging from the ceiling. All right, so I'm going to go with the banked turn for today. So we have a little picture, but the important things to think about in this picture are like what's actually going on. And so the car's going around this turn. And so here is your ground, but the radius, the center of the circle that it's traveling around is over here. All right, so if I were to draw my free body diagram, the forces that are acting on this car, I have the force of gravity and I have the normal force. Now, in this problem, there is no friction. If you had friction, that adds an extra element. It's going to be a little bit more math, but the ideas stay the same. If you had friction, it would be going up the side of this of the hill. Okay, so just two forces. Now in this, the angle of this track is 22 degrees, which gives this angle here to be 22 degrees. I'm just going to call this theta. Now, I don't like using this angle just for my personal preferences, so I'm actually going to do this problem using this angle here, which I'm going to call phi. All right, so first things first, we need to we drew a picture, we drew a free body diagram, so we'll need to sum the forces in the radial direction. Now, here's the center of our circle, and so the radial direction is anything that is along that, that line. And so the force of gravity is perpendicular to our radial direction, so it does not contribute to the centripetal force. Part of the normal force is pointed in that direction, so the sum of forces in the radial direction will be our normal force in that radial direction. You could think of it as this little piece here, FNR. Now, using sines and cosines, I see that that's my adjacent side, and that way I can rewrite this as the normal force times the cosine of phi. All right, now at this point, we can use Newton's second law. Some of the forces in the radial direction is the centripetal force, which is mass times the centripetal acceleration, MAC. In this problem, we have, we're asking what velocity should the car travel, and so that is asking for the tangential velocity. All right, so mass times the tangential velocity squared over the radius gives us the normal force times the cosine of phi. Now, at this point, we're stuck because we don't know how big the normal force is. So when you get stuck, the next thing to do is to sum the forces in the other direction. So we've summed it in the radial direction. Now we'll sum the forces in the y direction. Now, the car is not accelerating up and down, so the sum of the forces in the y direction will be equal to 0, which will then say that our force of gravity will be equal to the y component of the normal force, this side, Fny. I can then use my trig functions to say, okay, well, the normal force in the y direction is just Fn sine theta, or sine phi is my angle. So mg is my force of gravity. So my normal force is mg over the sine of phi. Now I can take this and plug it right in here for my normal force. So I get mass times the tangential velocity squared over the radius is mg over sine phi times the cosine of phi. Masses will cancel. Depending on what we're looking for, this is where we can start to solve. But the one thing that I would like to point out is that I see a cosine in the numerator and a sine in the denominator. Remember, sine over cosine is tangent. So this will give me g over the tangent of phi. Now, just something to think about here. If you had defined the other angle, if you had used theta, if you'd used our 22 degrees here, then this equation looks a little bit nicer because your tangent will be in the numerator. So this is the same thing as saying the velocity tangential squared over the radius is g tan theta. All right, so either one of these will be correct, where theta is this 22 degrees, it's the angle of the ramp, phi is 90 minus theta.